Hello everyone, I'm Qiaolong, a second-year PhD student with supervisor Dr. Yan Weifu from School of Data Science, Fudan University. Following Chenjie's talk, I will spend 25 minutes giving a talk about image inpainting and editing with various prior guidance. I will introduce more various prior for image inpainting and editing. First, let us review what our tasks are. The first task is image inpainting, which aims to fill missing region of images with semantically consistent and harmoniously textured contents. The second task is image editing, which involves the transformation or alteration of a photograph using various methods and techniques to achieve desired results, and we will focus on text-guided image editing in this talk. As introduced in Dr. Yan Wei's talk, priors are a form of guidance, guiding the generative model to generate the image we desire. And there are many more priors than we thought. Taking an image as an example, we can extract low-level images by filtered or well-formalized from deep neural networks, as we have done in the ZITS. Besides, some edge detection networks can extract boundary-aware edge from image, such as HED, CAT, and DXI, NED. What's more, previous work also used low-resolution images, segmentation maps, histogram of oriented gradient, Hugg gradient, and relative total variation, RTV, as priors. As there are so many priors we can choose from, so a natural question is, which prior combination can benefit our task most? Built upon our ZITS, we propose an improved zero-RA-based incremental transformer structure inpainting framework, ZITS++, and our model achieved much more improvements compared to Llama in high-resolution 1K inpainting results. We further compare different edges for inpainting based on our ZITS. Note that CAT edges have much clearer boundary structure and ignore high-frequency texture, but can produce many meaningless edges from texture region in column B. The CATs give meaningful holistic structure and can be well recovered by our model to improve the inpainting. So we use the learning-based edge CATs instead of the canny edge in our final model. We further compare different priors for inpainting to find the best prior for inpainting, which qualitative results compared with different priors in this figure. For each group, the first row indicates mask image and restored priors, while the second one shows inpainting results with no prior or different priors. All priors can improve performance based on the baseline. Hugg and low-resolution images have discouraged improvement without proper structure. Our previous ZITS, canny plus line, gets moderate improvements compared with other priors, whereas the three learning-based edges can achieve better results according to image quality. Furthermore, CATs enjoy the best performance among the three learning-based edges. Moreover, semantic segmentation works well, but we have only reported the upper bound of semantic performance here due to the extraction gap of segmentation results during training and testing. To capture holistic structure for high-resolution images, we should upsample the inpainting priors to target resolution. Both line and canny edge can be upsampled by SSU of ZITS. To upsample the learning-based edge, we introduce edge non-maximal separation (ENMS) to filter uncertain edge prediction. Then, the filtered edges are further binarized. Thus, SSU can iteratively upsample learning-based edges as lies. ENMS significantly eliminates ambiguous blur and artifacts near the boundary and improves the performance during high-resolution inpainting. However, other priors suffer from artifacts in boundary during resizing during the high-resolution inpainting as in the bottom figure, so we choose CATs, line, and gradient for low-resolution inpainting, and use CATs and lines for high-resolution inpainting. The whole pipeline of ZITS++ is illustrated here. Given mask image IM, mask prime P and binary mask M. We concatenate and input them to the transformer structure restoration TSR model for restored primes. Note that the prime of learning-based edge are directly produced by TSR to avoid information leakage. Then, gated convolution-based structure feature called SFE, which has multi-scale feature from restored primes. We incrementally add this feature into related layer of Fourier texture restoration FTR with Fourier convolution by the residual addition of zero initialized tunable parameters. Besides, it has been well explored that large receptive fields are important for image implanting, and FFC used in Llama has a global receptive field in the frequency domain. However, FFC failed to learn reliable feature relationship between masked region and unmasked ones. On the other hand, various attention mechanisms with long-range dependence are also incorporated into many implanting methods. But this attention-based method inevitably overfits a certain resolution without scale invariance. To unify the advantage of both scene and attention, we propose to inject the large kernel-based convolution into FTR. We follow the visual attention network to decompose the LKA with depth-wise convolution and point-wise convolution as in the figure. LKA are incorporated into up-sampling and down-sampling blocks of FTR, which are orthogonal to FFC. Because LKA devotes to learning better feature representation for masked region with a large receptive field, FFC tend to facilitate the global learning for regular texture in the frequency domain. Furthermore, we also use shortcuts with 3x3 convolution as FFN feed-forward network to ensure the generalization of LKA. We finally provide some object removal instances in large image from 1K to 2K resolution compared with Llama. Note that our method outperforms Llama in scene with weak texture. Our method can also achieve results with less blur that benefited from precise structural constraints. For the larger case with 2K image size in the bottom figure, our method can still get more consistent results compared with Llama. The primes we just discussed are all predefined. So, how about data-driven primes? In this paper, we propose to use prime learned from large-scale data through training of masked autoencoder to enhance the image implanting. This paper is accepted by ECCV 2022 and all code models have been released in this link. Although image implanting has achieved significant advances in recent years, we fail to tackle complicated high-resolution implanting situation with a limited capacity and a receptive field of a simple encoder-decoder model. So, we propose to guide the image implanting with an efficient masked autoencoder MAE pre-training model, which is called as Prime Feature and Attention Enhanced Restoration (FAR). Our motivation is that learn good primes from pre-trained models and leverage such informative primes for high-resolution image implanting, and there are few discussions about representation learning for image implanting. Let's first review the method of MAE. The structure of MAE architecture is shown on the left. It randomly masks the image patches and sends the unmasked patches into the encoder and decodes them to reconstruct the original image. As it only learns unmasked patches for the large variety encoder, the autoencoder can be pre-trained efficiently. Besides, the high portion of random masking achieves good performance in the classification, object detection, and segmentation tasks. Although MAE has blurry results with MSE loss shown on the right, features of MAE still benefit downstream tasks a lot. Our pipeline is shown here. For the given mask image, The MAE is applied to encode the prior features, and we resize the prior feature to 1/2 of original image size, and concatenated them with the Cartesian spatial grid. After that, the feature is encoded by a gated convolution and added to the encoder of attention-based scene restoration (ACR), which is used to restore the original masked image. Moreover, we leverage mean attention scores from the MAE decoder to aggregate unmasked feature to masked region in ACR and achieve the final impending image. First, the random mask used in standard MAE is not amenable to impending. Because the random noise mask is too easy to impending, we usually encounter a large continuous mask during impending. So, we blend continuous mask and random mask, while the total mask rate remains at 70 and 5%, and the mixed masking strategy can improve the learning of prior attention. Besides, MAE takes 16 times 16 token as input, so masks have to be enlarged as they are downsampled to 16 times 16. Should we fine-tune the MAE decoder with partially masked patches for more improved informative input? No, we found fine-tuning for partially masked patches causes overfitting. We think that the fine-tuned MAE learns more explicit results, which makes the scene restoration overfit MAE features. So, this enlarged mask region increases training difficulty, and can be seen as noise regularization. Thirdly, to overcome impending tasks with arbitrary resolution, the local feature example is leveraged to facilitate the feature warping from MAE to ACR in various resolutions, and we can get an additional 2D Cartesian spatial grid can further improve performance. Furthermore, we use gate convolution to filter useless features. To integrate prior feature into ACR, the general solution is to element-wise add upsampled prior feature to downsampled one of ACR. However, we observe an unstable training process with the vanilla element-wise addition as shown in the figure A. We try to multiply tunable parameters to the prior feature for the element-wise addition to ACR encoded features in various resolutions respectively. Moreover, a population study of the tunable parameter initialized with 0 and 1 as shown in figure A. The 0 initialization enjoys a much more stable convergence. Therefore, the 0 initialized addition is adopted in our model. We further analyze the tendency of different parameters trained in figure B. From figure B, both high-level and low-level features are important for the prior learning, since the absolute value of corresponding parameters are large, and the middle-level feature corresponding to alpha 2 seem to have less effect during impending. Compared to tunable contextual attention model of impending models, prior attention from MAE can better benefit the impending models. Visualization of attention from MAE and learning by contextual attention mechanism are shown in the figure. For the visualization of attention maps, unmasked regions are ignored as black, and the patch attended with the highest attention score is shown in masked region. Attention palettes are shown in the upper right corner of the first instance, which illustrates the exact position attended mostly by masked patches. Attention scores for MAE are more consistent and reasonable compared with learning-based contextual attention. Specifically, some irrelevant patches are attended by masked region in the contextual attention, which leads to confused attention maps. Besides, although some MAE results are blurry, the attention relationships are still effective. Here are the qualitative impending results. Compared with other methods, our method can obtain better results in both structure and texture. Furthermore, our model showed prominent improvement in structure recovery compared with Llama for qualitative results in rats. Other compared algorithms fail to reconstruct reliable semantics for certain objects in high resolution, such as the cup, necklace, and the temple in the right figure, except our method. Such good results are benefited from informative prior feature of MAE, which make the model understand the real category of objects in high-resolution cases. For face images, our method can achieve stable impacting results with consistent eye gaze. We further provide some 1K results on the right, which show that MAE can provide impressive price for both structure and texture reconstructions. More high-resolution results also indicate that MAE feature can provide good global receptive fields, even in 1K and 2K cases, and our model outperforms other competitors according to user studies. Finally, our MAE is frozen during training, which only affects a little to efficiency of the impending model. So far, we have discussed the various price. The next question is, can we combine the price with texture conditions? In this work, we study a novel task on task-guided image manipulation on the entity level in the real world. The task imposes 3 basic requirements: to edit the entity consistent with the text description, to preserve the text irrelevant regions, and to merge the manipulated entity into the image naturally. To this end, we propose a new transformer-based framework based on the 2-stage image synthesis method, namely many-chance, which can not only edit the appearance of entities but also generate new entities corresponding to the text guidance. This is the architecture of our many-chance framework for entity-level text-guided image manipulation. The basic idea of many-chance is to manipulate only the image token which corresponds to the text. Many-chance adopts transformer as the generation model, which takes the input text token and visual guidance token, create a sketch image generated from the input image as input, and generates image token autoregressively. Besides the classification loss on each token, many-chance adopts a semantic loss to help the model capture the visual semantic alignment between the input text and the manipulated image in the training phase. In the inference phase, many-chance adopts a semantic alignment model to locate the text-relevant token to be manipulated, and the generation model manipulates only these image tokens. The visual guidance is optional and is necessary in the case of editing only the appearance of an entity. We will detail each component within it. During the training phase, a transformer takes input as text and image token sequence and predicts the token autoregressively. The semantic loss of the many-chance is computed with the generated image and text by CLIP, a contrastive language image pre-training model. This semantic loss further boosts the semantic alignment between text and image, and is complementary to token-wise classification loss as a pixel-level supervision signal. As for the semantic alignment model, it accepts an original image and a textual property. 2 steps follow. In the first step, the model uses entity segmentation to recognize each entity on the image. In the second step, it selects the entity of highest similarity with the property by flip. A CLIP-style model optimizes with similarity from more tokens. During the inference phase, the transformer only regenerates the image token of selected entity and decodes the new image token sequence into the manipulated image. Note that the visual guidance sequence of the gray image provides the entity shape plan is optional. It's necessary in the case of editing only the appearance of an entity. This is the result of manipulating multiple entities according to different tasks with many-gain, lightweight gain, and our many-chance. Our many-chance can manipulate different entities accordingly. While 2 baseline methods fails, It shows that a previous method can only manipulate the texture or color of an object, while they fail to generate reasonable entity-level manipulation results from the test descriptions. This figure shows the manipulation from bird to flower and flower to bird on a mixture of CUP and Oxford. Many chains generate reasonable manipulated entities, which are corresponding to the text and fit the background, in both bird to flower and flower to bird setting. For example, in the third column from left, many chains not only generate a flower consistent with the description, but also complement the upper left corner of the manipulated flower with a leaf, which shows that many chains also learn the combination of the object information and the background. That's all. Thank you for listening to the talk.